Good afternoon to all of you. I am Shashi Kumar, faculty in Indian Institute of Remote Sensing. Today we are going to have a session on microwave remote sensing. Particularly here we are going to talk about synthetic aperture radar remote sensing technique. So synthetic aperture radar remote sensing technique is an active imaging microwave remote sensing technique which is carried out in the microwave region of the electromagnetic spectrum. So when the word is coming microwave remote sensing, it means that we are going to talk about the remote sensing which is carried out in the microwave region of the electromagnetic spectrum. And this remote sensing is carried in 1 millimeter to 100 centimeter range of the electromagnetic spectrum. When we are talking about the electromagnetic radiation, the electromagnetic wave will have one electric field vector, one magnetic field vector. Both will be perpendicular to each other, and they will be mutually perpendicular to the direction of propagation of the electromagnetic wave. Like here, if you will see, E and M are representing electric field vector and magnetic field vector respectively. Both are perpendicular to each other, and they both are mutually perpendicular to the direction of propagation of electromagnetic wave, that is represented by C. So here we can see the propagation of an electromagnetic wave. Now when we are talking about electromagnetic wave, so this relation is very famous. Speed of light will be equal to the wavelength, multiplication of wavelength and the frequency. And the wavelength is the length of one wave cycle, which can be measured as the distance between successive wave crests, and it is usually represented by the Greek letter lambda. And frequency is represented here by nu. So both are inversely proportional to each other. When there will be increase in the wavelength, there will be decrease in the frequency, and if there will be increase in the frequency, there will be decrease in the wavelength, because speed of light will be considered as constant. This is the microwave band which is used in remote sensing. So we are going to see here the portion of the electromagnetic wave electromagnetic spectrum which is used in microwave remote sensing. So that portion is covering from K band to P band. So here if you will see, for Ka band, wavelength range is 0.75 to 1.1 centimeter. For K band, 1.1 to 1.67 centimeter. For Ku band, this is 1.6 centimeter to 2.4 centimeter. Now generally when we are talking about imaging sensors, imaging synthetic aperture radar systems or sensors, so generally imaging is preferred to do with X band. So if you will see the X band, so the wavelength range is 2.4 to 3.75, and for C band this is 3.75 to 7.5 centimeter, and for S band this is 7.5 to 15 centimeter. For L band, the wavelength range is 15 to 30 centimeter, and for P band this is 30 to 100 centimeter. Now what we are observing here, our observation is, if there will be increase in the wavelength, like here if you will see, when one will move from K band to P band, there will be the increase in the wavelength. But if you will see the frequency, so there will be decrease in the frequency. So one can easily see that there, if there will be increase in the wavelength, there will be decrease in the frequency, and frequency is related to the energy also. So there will be low energy for the long wavelength ranges. And one more thing I would like to tell, like when we are talking about the synthetic aperture radar sensors, so if the sensors are launched, so like in the case of optical multispectral data set, one sensor can provide the multi-frequency data set in the different spectral bands. But here in the case of SAR remote sensing, one sensor is generally designed with a completely monochromatic property. So the sensor and the SAR sensor is a coherent system. So this is one SAR system will be launched in one frequency range only, like one SAR sensor is going to provide the data set in one frequency range, because if suppose a sensor is launched with X band capacity, so for its entire time duration it is going to provide the data set in X band only. If I require a C band data set for the same area, then at that time I need another sensor, another SAR sensor to get the data set in C band. Okay, because one sensor can provide the data set in one wavelength range for the entire time period. Now, when we are talking about the microwave sensors, so again, microwave sensors are categorized in two categories: passive microwave sensor and active microwave sensor. A passive microwave sensor detects the naturally emitted microwave energy within its field of view. This emitted energy is related to the temperature and the moisture properties of the emitting object or surface. Passive microwave sensors are typically radiometers. So when we are going to talk about the radiometers, it means that when the word radiometer comes in picture, it means that that is passive microwave sensor. The imaging concept of passive microwave will be very much similar to the thermal remote sensing, because in thermal remote sensing also the sensor is going to collect the thermal infrared emission from the earth object, from the earth surface. In the case of passive microwave sensor, the sensor is going to collect or acquire the data set, or acquire the electromagnetic waves or the radiation which is radiated in the microwave region of the electromagnetic spectrum. There are several applications of the passive microwave sensor in meteorology, hydrology, and oceanography. So, the microwave energy recorded by a passive sensor be emitted by the atmosphere, reflected from the surface, emitted from the surface, or transmitted from the subsurface. So, with the help of the passive microwave data set, a variety of thematic applications could be done. In active microwave sensors, so active microwave sensors provide their own source of microradiation to illuminate the target. They are not depending on the radiation of the earth surface, or they are not depending on the any other source of energy, like in the case of optical multispectral. Here sensor will have its own capability to generate the electromagnetic pulses. So active microwave sensors are generally divided in two categories: imaging and non-imaging. The most common form of imaging active microwave sensor is radar, which is an acronym for radio detection and ranging. So radar sensors transmit electromagnetic pulses towards the earth's surface or the targeted object, and scattering take place, and the back scattered information will be received by the sensor for the imaging purpose. Non-imaging microwave sensors include altimeters and spectrometers. In most cases, these are profiling devices which take measurements in one linear dimension as opposed to the two-dimensional representation of imaging sensors. Radar altimeter is used on aircraft for altitude determination, and on satellites for topographic mapping and sea surface height estimation. Spectrometers are generally non-imaging sensors and are used to make precise quantitative measurements of the amount of the energy back scattered from target, and spectrometer data set are used to get the precise information of the back scattered energy, and this is used to find out the wind direction and wind speed, and the sea surface roughness also. When we are talking about synthetic aperture radar, so synthetic aperture radar is a form of radar that is used to create images of objects such as landscapes. These images can be either two or three dimensional representation of the object. Now, when one is asking about the microwave remote sensing, so we have already seen one can define it in very easy way. The remote sensing which is carried out in the microwave region of electromagnetic spectrum is known as microwave remote sensing. And if anyone is asking about the definition of SAR remote sensing, so SAR remote sensing could be defined as an imaging active microwave remote sensing technique which provides higher spatial resolution data set. Now, when we are going to talk about synthetic aperture radar remote sensing, so we should understand that SAR sensor or the electromagnetic waves which are used in SAR remote sensing is not sensitive to the color information. They are mainly sensitive to the structural and the electrical properties of the targeted object. Like here you can see in the background image, this is the optical multispectral data set of the true color composite data set for the San Francisco area, and the top image is the imaging with synthetic aperture radar sensor. So here one can easily see that no color information is present in the SAR data set. It is having only dark and bright patches. This is coming because the SAR sensor is mainly depending on the structural properties of the object, and the structure and those kind of structures which are going to contribute in high backscatter will appear very bright, like urban areas, and the structures which are smooth, and if they are going to contribute in very less scattering and more reflection, at that time the reflected electromagnetic waves will go away from the sensor direction. So those kind of objects are going to appear as dark object. Now, and if you will see the vegetation, like this is the park area which is appearing green in the true color composite image. So this is appearing as moderate, not very dark, not very bright. So we are going to get the different types of images, different type of scattering pattern, back scattering pattern from different kind of objects or features. We are going to see the radar geometry. So here the SAR sensor is placed at the bottom of the aircraft. So here you can see that aircraft is moving in a direction. The direction in which aircraft is moving, that will be the direction of the SAR sensor also. That is the forward direction of the SAR sensor also. That direction is known as the azimuth angle. So sorry, not azimuth angle, azimuth direction. So azimuth direction is the basically flight direction, the direction in which SAR sensor is moving in the forward direction. Now there will be another direction, the direction in which SAR sensor is transmitting electromagnetic pulses. That direction is known as range direction. So the range direction is the direction in which SAR sensor is transmitting electromagnetic pulses towards the Earth's surface. Now, if you will see, the one portion of the area on the Earth's surface is illuminated by the electromagnetic waves of the SAR sensor, and here you can see that one image has been created based on the visualization from the SAR data set, from the SAR sensor. So here one can see that the river body could be easily seen here, that is appearing as a linear dark feature. Because water is going to appear as completely dark in the SAR data set if there will be no roughness or no ripples in the water. So at that time it is going to appear as very dark. Now the portion of the illuminated surface which is appearing near to the nadir, like here you can see that this vertical line is joining the virtually joining the aircraft to the Earth's surface. This normal line is known as nadir line. So the portion of the illuminated area which is appearing to the nadir will be known as the near range. It means that nearest point of the illuminated area will be known as the near range, and here you can see that this is the far range. Basically this is the farthest point from the nadir which is illuminated by the sensor. So this name is given as the far range. So near range and far range, these concepts should be clear, because the data set will be acquired in between near to far range. So now here you can see that in the range direction data set is acquired, and here there is one more geometric parameter, that is the angle of incidence. Here one can see that angle of incidence is the angle between the between the incident electromagnetic wave and a normal drawn to the point of incidence or the point of contact. So that will be the angle of incidence. So this angle of incidence is going to vary if the terrain will be undulating. So these parameters are basically used to generate the back scatter images, and the angle by which SAR sensor is transmitting electromagnetic pulses. So this angle will be known as the look angle, and look angle minus 90 degree is going to give the depression angle, which is represented here by gamma. Now here we are going to compare different remote sensing techniques like LIDAR, optical multispectral and SAR. So currently LIDAR, optical multispectral and SAR all can the imaging could be done with the help of the airborne platform, spaceborne, as well as the ground-based sensors also. And when we will see the radiation, so since LIDAR and SAR both are examples of active remote sensing technique, so they both will have their own radiation. They are not depending on the sun's illumination. Optical multispectral is depending on the sun's illumination, because this is going to work on the concept of the reflection reflection of the electromagnetic wave in the visible and near infrared infrared channel from the earth object, and the information captured by the optical multispectral sensor in the visible and reflected infrared channel. Now when we are talking about the spectrum, so LIDAR is generally LIDAR remote sensing generally carried in the infrared region. Optical multispectral is carried in the visual and infrared, and SAR is carried in the microwave region of the electromagnetic spectrum. Now LIDAR will have the single frequency. Optical multispectral, from the name it is multispectral, it is clear. This will be the multispectral data set, multispectral and the multi-frequency data set. And SAR sensor, one SAR sensor is going to provide the single frequency data set, but when the multiple sensors of the different frequency ranges will be used, so at that time multi-frequency data set could also be acquired. When we are talking about, there are two advantages of SAR remote sensing. One is polarimetry and another is interferometry. So with the help of the polarimetric and interferometric phases, several information could be retrieved, and this has been widely used in the scientific community in the different thematic applications to retrieve bio and geophysical parameters with the help of the polarimetry and interferometry. If you will see the acquisition time, so LIDAR and optical LIDAR and SAR both could be operated in day and night, both the time, so that we can say that they will have the night vision capability, because they do not depend on the sun's illumination. And due to the dependency on the sun's illumination, optical multispectral is mainly depending on the sun's reflected light, so they could be operated only in the daytime. Now if you are talking about the weather condition, if the weather is cloudy, so LIDAR and optical multispectral, they will have the electromagnetic waves in micrometer. So in the micrometer wavelength range, they could be easily blocked by the top cloud cover, and due to the long wavelength ranges in centimeters, SAR waves could be easily be penetrating the top cloud cover, and they can provide the data set of the earth surface even the entire atmosphere is completely filled by cloud. This is list of few famous SAR satellites. RISAT-1, this was launched in April 2012 C-band. RISAT-1A has also been added. Now this was launched on 14 February 2022. Again, that satellite is launched in C-band by ISRO India. RadarSat-1, RadarSat-2 and RadarSat constellation mission. These all the satellites are working in C-band. RadarSat-1 is currently not working, and the RadarSat is the SAR satellite series of Canadian Space Research Center. IRS1, IRS2, InviSat C, Sentinel-1A and Sentinel-1B. All these satellites were launched in C-band, and RISAT-1C will be launched very soon because RISAT-1B has stopped working. So RISAT-1C will be launched to fulfill the gap which is created due to the absence of the Sentinel-1B. So these data sets are available in C-band. Sentinel-1A and Sentinel-1B dataset, these are the freely available to all the users. Even current data sets are also available, and their the temporal resolution is also good, so their repeativity is good, so one can get the data set for their study area with very good repeativity, so one can do the mapping and monitoring of the study area, their study area. Now another is the JERS-1, ALOS and ALOS-2. These satellites were launched in L-band, and currently ALOS-2 is working. JERS and ALOS, these two satellites are not working. After that, to fulfill the gap in the L-band satellite, ALOS-2 was launched by the Japanese Space Research Center JAXA. So JERS, ALOS and ALOS-2 were the mission of JAXA. Now another famous satellite is TerraSAR X and Tandem X. These are the satellites in X band launched by German Space Agency DLR. Now here we are going to compare the different wavelength and the frequency ranges of different bands and to see their advantages and their potential. So currently if you will see when we are talking about P band, so currently we do not have any satellite right now, but European Space Agency is going to launch a satellite, and the name is Biomass. So this satellite will be launched in P band. Approximate mean wavelength will be approximately 70 centimeter, and since the wavelength is very large, so it can penetrate the canopy cover also. It can penetrate even dense canopy cover, and it can provide the information of the complete object in the sense the complete structure of the forest. And since the wavelength is large, so it can penetrate the soil surface also, so it can provide the information of the buried objects also for the archaeological purposes, and it can also be used for the forest mapping monitoring as well as the information retrieval on the forest disturbances. If you will see the L band, so in L band with 23-24 centimeter wavelength range, large number of satellites have been launched, as well as several satellites are planned also, like CSAT, JERS-1, ALOS, ALOS Pulsar, ALOS-2, Pulsar-2, NISR L, Tandem L. So these are the satellites which are going to provide. Some of them are already providing, and few of them are going to be launched in future, like NISR and Tandem L. These are the future missions launched and will be launched by different space agencies. Like NISR will be launched by the NISR is a joint mission of NASA and ISRO. So this will be launched in 2024. This is L band, so this will have the good penetration capability, and it could be used for the different applications like forestry application, environmental monitoring, agriculture, geological and hydrological. So in different applications the data set could be used. If you will see the S band data set, so the wavelength range will be approximately 10 to 12 centimeter. So here also you are going to see nowadays a good number of satellites are there. NISR is the future mission which will be launched by again NASA and ISRO. So NISR will be the first mission for Earth observation, which is going to provide the data set in dual frequency range L and S band. So S band will be very much useful in the ship detection, ice mapping, oil spill detection, flood mapping, forestry mapping, and the crop classification. Now C band data set, if we will see, so the mean wavelength is approximately 5.5, 5.6 centimeter, So this has been widely used for the agriculture mapping and monitoring, and it has sensitivity to ocean features. It has also been used for the ship detection, and this is used for the sea ice surveillance also, oil spill mapping and monitoring. Since the data set is freely available, so this is also used for in all the thematic application in like cryospheric, solid state, solid earth, as well as forestry and ecology. In all the C band is used because Sentinel data set is freely available to all the users. When we are coming to the X band, so mainly 3 centimeter wavelength range is used. So with the help of this 3 centimeter, one will be able to generate very high spatial resolution images, and since the wavelength is small, so surface roughness could also be measured, and this could be used for the topographic mapping as well as the flood mapping and monitoring. And the satellites which are there in X band are Terras RX, Tandem X, Cosmo SkyMed, and RISAT2, PAJ, COMSAT 5, so and ICI constellation. So all these satellites are working in C band. Now this is the Indian SAR Earth observation satellites. So RISAT2 was the first satellite which was launched on 20th April 2009 in X band. RISAT1 was launched on 26th April 2012 in C band. This was the first satellite which was capable to provide the circular polarimetric data set, hybrid polarimetric data set in Earth observation, and there were several advanced mode also. And RISAT 2B was launched on 22nd May 2019 in X band. RISAT 2B R1 was launched on 11th December 2019 again in X band. RISAT 1A was recently launched on 14th Feb 2022. This is again the satellite which is providing the data set in C band, and this is the first satellite in the world which is successfully providing the data set in hybrid polarimetry as well as the circular polarimetry. Hybrid polarimetry and the fully polarimetry. In hybrid polarimetry, name is given hybrid polarimetry because it is going to use linear polarization and the circular polarization both to do the imaging, so that the name is given hybrid polarimetry. And NISR mission, it is expected that this will be launched in 2024. Earlier date was 2023, but the new date just a few weeks ago, the new date was given 2024. So this satellite will be the first satellite which is going to provide the Earth observation data set in L band and S band. Now when we are talking about the SAR data set, so we have seen the several advantages, but one should know about the requirement and need of the data set with the help of the images also. So the two images are used here. The first image is the false color, standard false color composite image of LIS4, which is approximately of 5.6 to 5.8 meter resolution. And the similar resolution after processing was there with RISAT1 data set also. This is the false color composite image generated with the help of the hybrid polarimetric RISAT1 data in RH and RV. Both the data sets are acquired over the Doon Valley forest ranges. So, and here we can see the risicity also. So, when one will ask about the visualization, direct visualization based on the color. So, since our eyes are mainly working in the visual range of the electromagnetic spectrum, so anyhow we are going to feel comfortable to do the visualization with the optical multispectral data set. But SAR data set is not only used for the visualization purpose, this is also used for the information retrieval. So what extra information we could retrieve, that I am going to show here. So from this image, the swath is approximately 25 kilometer by 25 kilometer. I took a subset from this image. So here you can see that one subset has been taken here. And you can see that like the top image is the one band of the LIS4, and the down image is the bottom image is the one polarization of the RI set 1 data. Now here just I would like to suggest you to focus on this barrage. So if you will see this barrage, so this barrage is clearly visible in the SAR data set, but this barrage is not visible here in the optical multispectral data set. But from our image interpretation skill, one can say that okay, since the this water is diverted from the main stream, it means that there is something which is diverting the water. So we can say that okay, now there is something to divert the water, but actually there is barrage. But due to the color informations, the because optical multispectral data set is mainly sensitive to the color of the object. So color of the barrage is merged with the background water, so that this is not visible in the optical multispectral data set. But if you will see the same data set in the same area in the SAR data set, so this barrage is clearly visible. Why? Because the SAR data set is mainly depending on the structural and the electrical properties of the object. So structural and structural property, if you will see that, so structure of the barrage will be entirely different than the background water. So and the electrical property of the water will be different than the barrage, so that here one can see that this barrage is contributing in very high scattering, and this could be easily detected in the SAR data set. Now another area is also there. If you will see, there is one more barrage here in this area, and the same barrage is not visible in the optical multispectral data set. Now I would like to suggest you to see this undulating terrain of the zoomed view of the main data set. So here one can see that the top image is of list 4 and the bottom image is of RI set 1, FRS 1 mode data. So now here if you will see that the complete topography is not visible in the optical multispectral data set. The optical multispectral data set is showing very less sensitivity towards the topographic variation or the topographic undulation. But here if you will see in the SAR data set, complete topography of the terrain is clearly visible. Okay, so several people they are preferring to use SAR data set to get the complete structural property of the hilly terrain or the undulating topography. Now we have seen the advantages. There is another advantage. So here we are going to see one example of the Sahara Desert. Just focus on the middle strip. So middle strip, if this was imaged with the help of the optical multispectral data set, so one can easily see that the golden sand could be visualized here. But if the same area was imaged with the help of shuttle imaging radar SAR-A, which was operated in L band, so it was the long wavelength range was able to penetrate the top sand surface, and it was able to interact with the subsurface, and one can easily see that the paleo channel could be easily detected. Paleo channel is easily detected with the help of the L-band SAR data set. So here we are seeing the soil penetration capability of the SAR data set. Now we are going to see the imaging from SAR data set. So this is an animation created by European Space Agency for Sentinel-1 data acquisition. So here one can see that SAR sensor is transmitting electromagnetic pulses towards the Earth's surface, and even in the cloudy situation and the fog and haze, it can easily penetrate through it, and it can provide the information of the Earth's surface. Okay, like the cities are appearing as a very bright patches here. Here one can easily see that cities are appearing as very bright patches even in the cloudy situation, and water body and all the other features could be easily detected in the SAR data set, which is not possible in the cloudy condition in optical multispectral data. Now again this is representing the SAR geometry, in which we are going to see the slant line geometry of the SAR data set, and here we can see the sensitivity towards the structure and the electrical property of the object. Basically, when we are talking about the resolution of the SAR data set, so basically there will be two resolutions. One will be the azimuth resolution and the other will be the range resolution. So length of a resolution cell in azimuth direction will be known as azimuth resolution, and the length of resolution cell in the range direction will be known as the range resolution, because we have seen that there are two directions, azimuth direction and the range direction. So due to these two directions, there will be two spatial resolutions within single SAR resolution cell. So the length of resolution cell in azimuth direction will be known as, like here if you will see that this length of this cell in the is in the azimuth direction. So this will be known as the azimuth resolution, and the green line is representing the range resolution, the direction in which the SAR sensor is transmitting electromagnetic pulses. So length of the resolution cell in this direction will be known as the range resolution. Now, the concept of synthetic aperture radar also we are going to understand here with the help of the point target. So actually, the actual antenna of the radar system will be very small. So with the help of a small antenna, we are synthesizing a large antenna from this actual small antenna. Now that synthesized antenna will be of several kilometers, and with the help of that one will be able to create very high spatial resolution data set. Like here if you will see, suppose this point target is first time detected during imaging. So suppose this is the first time to detect this point target, responses of electromagnetic waves from this point target. Now after that, SAR sensor will transmit the electromagnetic pulses from all the location, and suppose this is the minimum distance, this is transmission and receiving from the minimum distance, and suppose this is the farthest point. After that, this point target will not be visible for the SAR sensor. So what will happen? The SAR sensor will have the responses of the return signal from this point target from first point to the last point. When all the signals will be merged, so the entire distance traveled by the SAR sensor, radar sensor, to track this target is going to behave like a large antenna that is represented by capital L. Now here you can see that range resolution is inversely proportional to the antenna length. It means that smaller will be the amount of smaller quantity of the resolution will be high spatial resolution. So high azimuth resolution will be acquired when the antenna size will be very large. Now the range resolution is depending on the pulse width, that is represented here the C tau divided by 2. Azimuth resolution is the capability of the sensor to clearly separate the two objects in the range direction by getting the two separate responses of electromagnetic pulses in the range direction. Like here we are going to get an example. An example is given with the help of tau of it equals to 1 microsecond. For 1 microsecond, the distance will be, when it will multiply with the speed of light, the distance will be 300 meter. Now according to the formula, C tau divided by 2 will be 150 meter. Now here one can see that when the distance between the two objects is less than 150 meter, so the sensor is going to detect a large pulse, large return pulse, because here the sensor will not be able to get the two separate pulses from the two objects. So a large pulse will be detected, and these two objects are going to appear as single object in the SAR imagery. Now in the second example, what we are going to see, again for tau equals 1 microsecond, range resolution will be 150 meter, and now here one can see that this is 200 meter. Now in the case of 200 meter, here one can see that there are two separate pulses which are received by the sensor for these two targets. So both will be separated in the two cells in the range direction. So both will be appearing as two objects in the SAR data set. Since the SAR sensor is side-looking radar sensor, so there will be slant range ambiguity. So all the objects appearing in near range, they will be compressed in the air, shape and size. Here you can see that objects are the ground range images. Here objects are A, B, C, D, and their representation, graphical representation in the SAR data set is shown here. So here one can easily see that in the SAR data set they will be appearing as the compressed object. So when we will have the SAR data set, so our task is to remove or minimize the slant range ambiguity by converting it to the ground range. In synthetic aperture radar remote sensing, polarized electromagnetic waves are used because unpolarized energy vibrates in all possible directions perpendicular to the direction of travel, and imaging will become difficult. Now radar antenna send and receive the polarized energy. The polarization is defined based on the vibration of the electric field vector according to the propagation axis. So mainly here we are going to talk about the two polarizations, horizontal and vertical. When the electric field vector will vibrate vertically according to the propagation axis, then the polarization of the electromagnetic wave will be vertical, and if it will vibrate horizontally, then it means that the polarization of the electromagnetic wave will be horizontal. In this example, we are going to see the different polarimetric combinations which could be acquired from the SAR data set: HH, HV, VH and VV. So HH is representing transmission of horizontally polarized electromagnetic waves. Here you can see that horizontally polarized electromagnetic waves are transmitted, and at the time of receiving, horizontally polarized electromagnetic waves were received. So the combination became HH. Now VV means vertically polarized electromagnetic waves were transmitted, and at the time of receiving, vertically polarized electromagnetic waves were received. Now if you will see the combination HV, so the horizontally polarized electromagnetic waves were transmitted towards the Earth's surface, and after scattering, vertically polarized electromagnetic waves were received. So this combination became HV. Now similarly another combination will be VH. It means that vertically polarized electromagnetic waves were transmitted, and at the time of receiving, horizontally polarized electromagnetic waves were received. Now here you can see that SAR imaging is shown in this graphical way. So during image acquisition, SAR sensor can transmit the horizontal polarized electromagnetic waves. Here this is represented, this is transmitting horizontal polarized electromagnetic waves. When the bunch of the electromagnetic waves will hit the object, its polarization may be broken, and some portion of the incident electromagnetic wave in the back scattered signal will start vibrating in the vertical direction. So that will become the vertical polarization, and some will be, it might be possible that there will be some portion which will be unpolarized. So at the time of receiving, if the sensor is receiving horizontal polarized, then the combination will become HH. If the sensor is receiving vertical polarized, then the combination will become HV. So now here you can see that from single transmission of horizontal polarization, there is possibility to get two receiving channels, so that two polarizations could be received. Like two polarimetric channels could be generated from single transmission of the channel from the electromagnetic wave. So here you can see that the combination will become HH and HV. Similarly, for the single transmission of the vertical polarization, it will be possible to receive the horizontal component as well as the vertical component. So the combination will become VV and VH. Now this is the high spatial resolution data set of TerraSAR X, and as we have already talked about, the radar return about the terrains are mainly determined by the physical characteristics of the surface. These are the surface roughness, geometrical structure and orientation, and the electrical properties, that is mainly dielectric constant, moisture content and conductivity of the surface. So accordingly we are going to get the responses. So here in this image we are going to get the bright and dark patches based on their scattering nature, because from water there will be complete specular reflection, so that very less scattering will occur and very less information will be sensed by the sensor. So this is going to appear as dark, and all the objects are appearing moderate bright according to their structure and the electrical properties. Now surface roughness is defined based on the wavelength, radar and the depression angle. and the height of the object on the earth's surface. So the very famous criteria, Rayleigh criteria, is used to measure the surface roughness. Now this is the smooth and the rough Rayleigh criteria. The area with smooth surface roughness sends back very little back scatter towards the antenna, and it acts like a specular reflecting surface where most of the energy bounces off the terrain away from the antenna, that we had already discussed. The small amount of the backscatter energy returned to the antenna is recorded and shows up as a dark area on the radar image. The quantitative expression of the smooth surface criteria is given as object of height should be less than or equal to wavelength divided by 8 sine depression angle. It means that those surfaces which will be having the object height less than or equal to lambda divided by 8 sine gamma, that is going to appear as a smooth surface, and all the surfaces which will be having object height which will be greater than this amount, that will going to appear as rough surface. But that criteria was not working very well in all the condition. So the Rayleigh criteria was modified by Peake and Oliver. So Peake and Oliver modified Rayleigh criteria is given here. So according to that, a smooth surface criteria is object height should be less than lambda divided by 25 sine of depression angle, and for rough surfaces, height of the object on the earth's surface or any surface should be greater than lambda divided by 4.4 sine gamma. Now and if the object height will be coming in between these two, then that will be the intermediate surface. Now very interesting point I would like to show you here. Here one can see that there are three configurations given. Aircraft Ka band with wavelength 0.86 centimeter and depression angle 45 degree. Aircraft X band with wavelength 3 centimeter and depression angle 45 degree. CSAT L band with wavelength 23.5 centimeter and depression angle 70 centimeter. Now here you can see, just focus on the last point, the surface which is going to appear as rough surface according to this configuration of the SAR system, these parameters of the SAR sensor. So all the surfaces which will be having object height greater than 0.276 centimeter is going to appear as rough surface. It means that the object which will be having the height 2.7 greater than 2.7 millimeter is going to appear as rough surface. The same surface, suppose the object height is 0.5 centimeter, so the same surface is going to appear as a smooth surface for CSAT L band with the parameters lambda equal to 23.5 centimeter and gamma equal to 70 degree. Now all the other parameters you can validate from your end, you can calculate because formula is given. So intermediate surface, rough surface and smooth surface criteria for all the sensors you can match. Radar backscatter is function of angle of incidence. Also it is highly depending on the angle of incidence. Scattering will be very high in the low angle of incidence, like here in the both the cases, even for the smooth surface and the rough surface in both. Here you can see that in the near range high scattering, high amount will be received by the or sensed by the sensor, and in the case of rough surface also you can see that high amount of the scattering will be received in the near range in comparison to the far range. Now if the terrain is undulating, so for the undulating terrain we can see that when the theta means angle of incidence is moderate, so we are going to get the moderately bright patch or moderately bright signal. And when theta is here, angle of incidence is small, because here according to the look direction of the sensor this will become small, and when this will become small, so high return will be received by the sensor. Now again just opposite side of the slope, if you will see that here theta became large, so that very less information will be received for this side opposite face. So here you can see that this is going to appear as dark, and again for this location theta will be moderate, so moderately bright patches we are going to get. Now we are going to talk about the interaction of electromagnetic wave with soil. So dry soil, there will be high penetration, less scattering. So dry soil is going to appear as dark surface, dark object in the SAR data set. Wet soil, there will be less penetration, high scattering. So wet soil is going to appear as the bright feature in the SAR imagery. Flooded soil, when the entire surface will be completely covered by the flood water. So at that time, again, due to the high reflection and the less scattering, very less information will be received by the sensor. So flooded soil is going to appear as dark feature in the SAR imagery. One very famous scattering is the volume scattering. So volumetric scattering is related to the multiple scattering process within a medium, such as the vegetation canopy of a cornfield or a forest. So in the volume scattering, entire volume of the object is going to contribute in the scattering. Like when we are talking about the forest, so the top canopy surface, small twigs, then small branches, big branches, all are going to contribute in the scattering. Entire volume of the structure is going to contribute in the scattering. So due to that, the multiple scattering, the volumetric scattering will be retrieved. Here this is going to show the penetration capability of the different frequency ranges in for the forest patch. So here you can see that L band will have the long wavelength range, and for this coniferous forest it can penetrate up to the ground level, and it can provide the trunk information very well. In C band, frequency wavelength is small, so less penetration is there, and in X band very less penetration. Maximum return in X band is there from the canopy and the small twigs. Now the SAR data set is provided in the complex format, so that the phase and intensity or amplitude both could be preserved. So each and every resolution of the SAR data set will be represented by a complex number. So first portion is going to represent the real channel, and the second portion is going to provide the information of the imaginary channel. So with the help of this complex data set, one will be able to do the interferometry or the polarimetry for the various thematic applications. Now in the SAR data set, speckle is a normal problem because due to the interaction of the return signal, there will be bright and dark patches. So the constructive interference are going to appear as the bright noise, and sometimes they are going to create problem in identifying the object. Like here you can see that this is the again TerraSAR X data set for the Visakhapatnam. So due to the speckle problem, here you can see that we are not able to clearly visualize the object, because high scattering is a natural phenomena from the urban area. So from urban area we cannot identify that there is a speckle or not, but from water body it is easy to identify that this image is suffering from speckle. So here you can see that like this is getting problem in identifying the identification of boats and ships. So after doing the speckle filtering, now we are able to clearly identify the boats and the ships in the water. There are mainly three distortions in the SAR data set. These are the geometric distortions: foreshortening, layover, and shadow. So mainly distortions will be foreshortening and layover. Now foreshortening is graphically represented here, and it is defined as when the radar beam reaches the base of a tall feature tilted towards the radar before it reaches the top, foreshortening will occur. The slope AB will appear compressed, and the length of the slope will be represented incorrectly. So here you can see that A dash B dash, this slope will be represented incorrectly. So foreshortening effect is generally occurring in the far range, and here one can see that due to the foreshortening effect in this hilly terrain, we are not able to get the clear information of the slope. Now another is layover. Layover occurs when the radar beam reaches the top of a tall feature before it reaches the base. The return signal from the top of the feature will be received from the signal from the bottom. As a result, the top of the feature is displaced toward the radar from its true position on the ground, and the ledge over the base of the feature. So now at that time what will happen, we will not have any information of the slope, because the complete slope information will be covered by the top, even bottom will be caught by the top, so no, we will not have any slope information. Layover generally occurs in the near range of the SAR data set. Now here you can see that due to the layover effect, we are not able to get the any information of the slope in these imageries in the near range. Another is the shadow. Both foreshortening and layover result in radar shadow. Radar shadow occurs when the radar beam is not able to illuminate the ground surface. Shadows occur in the downrange dimension behind vertical features or slopes with the steep sides. So here you can see that just opposite to the object, there will be, if this object will face the SAR sensor, there will be shadow opposite side of the object. Now with the help of radar shadow, here you can see that we are in this image we are not able to identify the features, but if you will have the clear cut information, high resolution data set, clear cut information of the shadow, so with the help of the shadow one will be able to find out the object height as well. Now SAR data sets are acquired in mainly three modes: steep map mode, spotlight mode and scan mode. So in steep map mode, the sensor is fixed with a particular angle of incidence and it acquires the data set, and the data set will be appearing like steeps, and in steep map mode we are going to have moderate swath and moderate spatial resolution. Now in spotlight mode, SAR sensor will be focused on one small area during its entire imaging. Like here you can see that from first point to last point it is focused on one small area. So in spotlight mode there will be very high spatial resolution up to 25 centimeter, but the coverage will become very less, like 10 kilometer, 5 kilometer or 14 kilometer, like that. The coverage, the total swath will become very less, spatial resolution will become very high. Scan SAR mode is the mode in which using the SAR sensor will be operated in the different angle of incidences to cover a large swath. So in scan SAR mode we are going to get coarser resolution but larger swath, larger coverage. There are different formats: raw data, SLC data, multi-look data, geocoded data and polarimetric data. Generally for the scientific purposes, particularly for the earth observation, we are not preferring the raw data set, because generally space agencies are having the SAR processors to process the raw data set. This will be the part of the signal processing. The remote sensing community preferring to work with the SLC data, single look complex data set, so that polarimetry and interferometry could be done. If the data set will not be in the single look complex format, or if the complex information will be missing, polarimetry and interferometry could not be done. Now it is also possible to get the data set in the multi-look format. Multi-look format data set will have the data set which will have the the data set which will be free from the slant to ground range ambiguity, as well as the pixel shape will be also be in the square shape. Now geocoded data set will be the georeference data set. It will have the coordinate information. Now polarimetric data set, as we have seen that there are 4 polarizations: HH, HV, VH and VV. So if the SAR sensor is capable to provide only one polarization at one time, then that data set is known as a single polarized data set. If the SAR sensor is capable to provide the 2 polarimetric combinations out of the 4 combinations, then that will be known as a dual polarized. If the sensor is capable to provide all the 4 polarimetric combinations at the same time, so the polarization of the data set will be selected according to the application and the user's choice. Like this is the quad pole data set for the Yellapur forest area of Karnataka. So here you can see that this is the sigma naught image, a radiometrically calibrated image of HH polarization. The second one is of VB polarization. When you will go in detail, then only you will be able to find out the changes. And again, these are the HV and the VH polarization. So these 4 polarizations, they will have the 4 different images in different polarizations. So it means that each polarimetric combination will be represented by one image. Now this is the false color composite image generated from the polarimetric modeling approach. So here one can see that the volumetric scattering is represented here in green color. Double bounce scattering is represented in the red color, and the surface scattering or the single bounce scattering, which is mainly contributed by the water or smooth surface, this is represented in the blue color. Now there are several advantages of SAR remote sensing. Now we are familiar with these advantages, and these are listed here. Cloud penetration capability to provide all weather data, night vision capability due to the active radar sensor, sensitivity of SAR signal to structure and dielectric property of the earth objects, polarimetric and interferometric phase to provide the precise target information for different applications. And there are different applications of SAR data set for SAR interferometry for DM generation, for subsidence mapping and monitoring, SAR for cryospheric and glaciological application, SAR for soil moisture, SAR for structural and biophysical parameters retrieval, SAR for crop mapping and monitoring, SAR for flood control, SAR for volcanological application, SAR for oil spill and the ship detection, and there are several others which are not listed here. And to find out the below ground information of the buried object, SAR sensor can provide up to certain extent to get the complete information. Ground penetrating radar systems are operated. So this is GPR, which is operated. Ground penetrating radar systems are operated to find out the subsurface information. Like this is image. This animation is showing the how the information is retrieved when the longer wavelength ranges are used, how much clarity is there in the subsurface feature identification. Thank you. I have covered my lecture. Now very soon we will start the question answer session.